Hello. So first of all, let me say thank you to the organizers of the QPL conference for accepting this unscheduled talk. I will be talking about a topic that came out of thinking together two seemingly not necessarily related topics, which is quantum cellular automata and quantum gravity. This is a collaboration with Pablo Arrighi and Amelia Durbec. There is a version on the archive. The talk is partly based on an updated version submitted to QPL, which should appear also soon on the archive. And the talk title is Quantum Superpositions of Graphs. Okay, some motivation from General Relativity is the following. The central insight of general relativity, the big idea that Einstein used as an organizing principle to formulate the theory, in particular, writing down the action, what is called the Einstein-Hilbert action, is a very simple idea that nothing that is physical or real should depend on coordinates. Mathematically, this is expressed as invariance under diffeomorphisms, smooth transformations of the manifold to itself. Now, the more metaphysical idea or philosophical idea is that whatever is in the theory that is serves as a background, as a canvas on which the physics will play out, is a mathematical object, and the physics should not depend on that. In other words, to do differential geometry, you need some sort of amorphous blob, essentially a set with certain properties of continuity that make it differentiable and so on. And in particular, from the famous Hall argument, if you're not familiar, it's a nice discussion to look up. It follows that the points of the manifold do not represent the points in space and time. So events are not points on the manifold. They are defined, in fact, as space-time coincidences. So you add this idea of test particles, not gravitating particles in the theory, and when they cross, that's when you say that there is a physical event, that something that happened in a specific spatiotemporal vicinity, and you do not identify it with the point on which it sits, because that's what can change under a diffeomorphism. You can move it around. So how does this relate with coordinates? Well, in particular, we lay coordinates first on the manifold. That's before we put anything that might have a physical interpretation, like a physical field. And changes of coordinates are in one-to-one correspondence with these smooth transformations called diffeomorphisms. All right. Now, the idea of the talk is to think of this idea of background independence in a discrete setting, in a genuine discrete setting, in the sense that now this canvas will be a graph, which we do not want to embed in a continuous background, a manifold, in order to make sense of things. We want to live with this graph alone. And the question is, shouldn't we again demand that physics should be invariant under coordinates? And what are coordinates now? Since we are not embedding this back into a continuous space, we want to do everything in this discrete setting. What are coordinates? And obviously, coordinates are the names we give on the nodes. In the continuous, you can think of laying coordinates as essentially giving names to each point of the manifold. If it's a four-dimensional manifold, it's going to be a quadruple of names like X, Y, Z, W. And changes of coordinates are renamings, which are graph isomorphisms, another way that they are known. And so we want, the point of view taken here is that our canvas is the graph. We're not embedding it again in a manifold, in which case also the links that connect to nodes would become curves of this manifold. We really just have nodes. They may be linked or not, which we can think as a topological notion of adjacency. But there isn't anything more to a link other than saying us whether there is a connectivity between two nodes, and all that's needed in terms of names or coordinates are really the node names. For instance, a link that connects a node A and B would be link AB. You do not need a new name for that. All right, let me insist a bit further on this because this is a point of, can be a point of confusion, that names are really the canvas in the same sense that when you have a manifold and you lay coordinates on it, really that's a way to describe the manifold. We haven't added yet anything that might be physical, any fields. In particular with graphs, a confusion we're trying to clear up is that usually we color graphs in applications with whatever coloring might be appropriate for the application at hand. For instance, in quantum gravity, often it's invariance of representations, for instance, spins that would label certain representations of a group, like spin networks in loop quantum gravity. Now, the first point is that there is no way to define a graph in the generic case without using names. This is not really different, but is less obvious in manifolds because often we use the same manifolds for many applications. And the difference between manifolds is in their topological properties, as with graphs. So that will be whether they have a boundary and whether there are holes in the manifold. Now, graphs, there are much more graphs that one might consider. And except if it has some specific symmetry, like saying the maximally connected graph with 5 nodes, you cannot define it with in an abstract sense. You need to put names in order to write an adjacency matrix, like a matrix that has all the names of the nodes as columns and as rows, and putting a 1 on the corresponding slot if the 2 nodes are connected, and so on. Excuse me. Right. So we are right now at the level before we have put any physical fields on the graph. There is only the names of the graphs, like coordinates of the manifold, and we can postulate a Hilbert space going to quantum theory directly, where the Hilbert space is postulated to be spanned by a countable basis, is spanned by graphs. In particular, we postulate that the graphs form a countable basis of the Hilbert space. And one state would be of this form that I give here. This is a pure state, could be a mixed state in general. And essentially, what we want to understand is how do you make sense of adding graphs like that in a superposition. Now, the question that immediately arises is, what do we do if two graphs are related just by a renaming? Do we take them to be the same graphs? Do we take their inner product to be unit, or do we take them to be orthogonal? In order to define a Hilbert space, it's not enough to have a basis. You need to have a definition for your inner product. Now, if we take two graphs that are related by renaming to be unit, to be the same graph, then essentially we have already removed names. And we have a state space that is at the level of anonymized graphs. Now, note that an anonymized graph, or abstract graph, as sometimes is called, is a less primitive object than a named graph. You have to first name a graph. Essentially, a graph is a named graph because there's no way to define a generic graph without names. Then take all renamings and then take the equivalence class of all these graphs to be an anonymized graph represented by any given graph that is named, that is in this equivalence class. Now, if we take them to be orthogonal, it sounds strange because we're taking two graphs that are the same except from names, and we take them to be now different. This is obviously a coordinate dependence that we will need to then remove somehow. And however tempting it is to do this directly by taking them to be the same, in fact, this talk is dedicated to arguing that we should, in theory, take two graphs that just differ by name to be different graphs, and then remove names in what follows. Now, we will see this with one specific example, which lays out the ideas and why I'm saying that two graphs that are named differently should be taken at the mathematical level to be different graphs. The Hilbert space is now includes coloring. You imagine that we take this Hilbert space that I talked before that is defined at the level of not colored graphs, and then you can extend it by adding colors, so adding internal states to the nodes. Our Hilbert space is for a 2x2 complex matrix at each node for any given graph. And we will define dynamics in the sense of quantum cellular automata by a unitary that is acting the graph and decomposes locally to local unitaries, U, which is one step of the dynamics every time you apply U, and is given by the product of the following two operations. H is applying a Hadamard operation on each node on the internal state, and T is acting like a shift, where you take a particle and you move it to the node that is next. Now, I'm giving a graphical notation of how this works. On each node, there are four potential states, which is no particle, a B moving particle, an A moving particle, and both an A and B moving particle, and there are no collisions. So no particle, B moving particle, A moving particle, A and B. You will note that I have these small A's and B's here. These are called ports. They're not names of nodes. The names of nodes are what you can see here, this U, V, and W. And you can think of this as a way to keep track of the fact that there are two directions, like left and right, but in the sense that it doesn't matter what you call left and what you call right. The only important thing is that there are two possible directions at each node. Now we're taking a very simple example here. The state space is taken to be only graphs that have two valent nodes. And we will act in particular to this initial state with these dynamics and see what happens. Okay, so to create one step, we need to first act with H and then act with T. Acting with H simply takes a name moving particle. This is our initial state, which it's a circle with 4 nodes. Takes a name moving particle to a superposition of an A and B moving particle on the same node. As you can see with the name here, it's a node W. And then applying T, will move these particles according to whether they're A moving or B moving. So for this branch, it's going to move towards the A direction, go to node V, and here it will move from in the B direction, go to node X. That is one step of the dynamics. This is U. Now, if we do this again, we do U 2 times. It's an easy exercise to use this formula here to see that we get this superposition of 4 branches, where now we have 2 branches with an A moving particle, this one and this one. There's a A moving particle here and an A moving particle there. Both are with plus, come with a plus sign, and then there is 2 branches that have a B moving particle and come with an opposite sign. Okay, so this is what we get from this dynamics. Let us try this now again with anonymized graphs. Graphically, it's easy to see what would happen. Essentially, as we saw just now, the H operation does not move anything. It's just acting on a node and creating a superposition of an A and B moving particle. If you start with an A moving particle, what is moving along nodes is T. However, if we now anonymize, essentially T will be doing nothing because these 2 graphs that have a B moving particle at V and a B moving particle at W, the node name W, will now be taken to be equivalent. So H is only acting on a node, T is not doing anything. So doing U twice, TH essentially is going to give us H squared, which is the identity. So we are back to the state we started. Okay, so now we have 2 very different situations. If we use names, we get both B moving and A moving particles. While if we use anonymized graphs, if we act on equivalence classes and the renamings, then we only get A moving particles. Now, in this Gedanken experiment, what that means is that local measurements can differentiate between the 2 dynamics. These are different physics we're talking about. So now we're left with a conundrum. What do? We want to allow the situation that we had before. In fact, this is a very simple and known quantum world that has applications that's been implemented in a laboratory with beam splitters and photons. We seem to be getting the wrong result. There's something very silly going on here. And names help you to keep track of what is happening. Essentially, if you think about it, names help you keep the alignment of the graphs. This fiducial information helps you to know that, oh, this is the node where I started from, that was called W. If you remove that information, then there can be symmetries, like in this example, that make things cancel out. So names are useful for this, for aligning graphs. Okay, but do we really need names to do this? Can we use something else, like setting a landmark, some external reference, the lamp walls or the fixed stars? All right, so let's see how this would work if instead of using names to align the branches, we would use a landmark, which is this red, this green color that I have here. So this is another, an internal state that we add in addition, some more information that we're adding in our dynamics, in our kinematics in particular. This is fixed and stays there forever, so that we can do without names and work with anonymized graphs. It's easier to see if it's on a straight line. You can think of this as exactly the same dynamics we had before, but applied on a larger cyclical graph. And we're looking at a piece of it. Or you can think of it as an infinite chain. That would also work, but it would take us outside the formalism we used in the draft on which this talk is based. We are only working with finite graphs. That means with a finite number of nodes. The mathematics would change if we had an infinite number of nodes, but the moral would stay the same. Okay, so what's going on here? We're applying U twice. It's exactly what we're doing before. So in the first step, there will be first H, then T. There will be one particle here, one there. Then you do it again, and this will take one particle here, one there, one here, one there. So you would have two at where you started from, and two that are 2 steps away. And we see that because there is this color here, this allows us to make sense of exactly what I just said, that they have moved 2 steps on the left and on the right in the A and the B direction. If this green color wasn't there, because these are anonymous graphs, the first branch would be the same as the third one, and the second one would be the same as the fourth one, and this would cancel out because of the sign, and we would have gotten this, as we just saw before. Now, the issue is that this landmark that we've put, whatever we want to interpret it to be, could be arbitrarily far away. And what that implies is that with local measurements, imagine having agents on each node identical with identical apparatuses, and they can simply detect whether there was or there wasn't a B-moving particle. Here we do have B-moving particles. We have this one and this one. Well, here we don't. So just by detecting a B-moving particle, they would know whether the landmark was there or not. Now, think of this as detecting whether you see up and down particles. You can do it repeated times and see if you see both kinds. You don't need to know what up and down means, just so long as you have 2 kinds of particles is enough. Now, this is a problem. This is some type of instantaneous signal that we have here. This has to be qualified. What do you mean by instantaneous signaling? Because I haven't told you that there is really a notion of distance in terms of space-time distance, not necessarily, but obviously you would run into trouble even for very simple applications, including trying to describe the implementation of these dynamics on an optical table with beam splitters. You would get it wrong if you weren't using either a landmark or names. And landmarks have come with this issue that you hard code in your theory that you can, with local measurements, detect what is happening very far away. Okay, now let me do the devil's advocate. Is this all too simple to matter? Well, it matters because it is too simple. This is the simplest example of a quantum bulk, and we already ran into this trouble. So imagine now that you want to have some sort of fundamental theory based on these ideas of quantum cellular automata. on quantum graphs, what do? In principle, now you can have very complicated dynamics. You can have any initial state you want, and you have to worry about an arbitrary number of steps, not just 2 steps after. What do? Do you check every time that this type of issue does not arise for every dynamics initial state and number of steps? Or do you just put enough landmarks to be sure this issue will not arise? For the generic case, you will end up putting landmarks everywhere, which is not unlike putting names everywhere. So let us go back to the classical theory in general relativity. It's actually similar. To have a notion of an event, you need a coincidence between test particles. So if you want to make sense of space-time localization everywhere, then you will end up putting coincidence all over the place, and they will have to be distinguishable test particles. And this is fine as an interpretation. This is how the world is. In practice, however, what you do is that you use coordinates. Now, is this trouble using coordinates? Well, no, actually it's not, because of how we do physics with mathematics. By not insisting of trying to landmark things, you just see that removing coordinates is actually a very powerful symmetry of the theory, which can be very useful. As we said in the beginning, that's how Einstein came up with general relativity, by realizing that by postulating coordinate invariance, I find a very powerful symmetry that tells me how my theory should look like at the level of the action in particular, in that case. So this is what I'm suggesting. Why not postulate this symmetry principle, renaming invariance, in the graphs? And in particular, we have seen that I have been talking about the quantum case. It carries through very easily, which is not evident how you would do in the continuum, just because diffeomorphisms are complicated things. Although Lucian Hardy has certain attempts recently, and other people, there's Philip Horn's line of work as well. In particular, what this would help you is how to align superpositions of graphs and recognize observables of them. What are the real physics that play out on superpositions of graphs? And I leave you, this is the final slide. This is how we formulate renaming invariance, by saying that observables O are those that satisfy this relation. The U dependence makes them local observables. This is a name, U, and excuse me. What this comes down to is essentially to demand that O of R of U is equal to, excuse me, right. So O of R of U times R is equal to R times O U, because the renaming R is a unitary and will cancel out. A renaming acting on a given graph is an injective function, so by trivially extending it over our orthonormal basis of graphs, it becomes a unitary. And I leave you with a question. Having at hand a good definition of renaming invariance, can we now use this and learn what are the good observables for agents living on superpositions of spacetimes, which is a very active field of research right now. Many people are thinking about superpositions of spacetimes, and the obvious question that arises is, what does it mean to make a measurement in such a situation? Having an agent living in the superpositions of spacetimes, there is a quantum reference frames developed by Czaslav's group at Vienna, and so on. So I'm happy to take your questions in the chat. Thank you for your time.